Okay, so I'm gonna try this. This is my first time trying this in my bedroom. So anyways, motion word problem with headwind or current. So you guys are all quite familiar with motion word problems. They were so far you've only learned the fairly basic ones. But there are sometimes problems where you are like you have a boat and the boat is traveling down a river and the boat may be going a certain speed in relation to the water, but in relation to the land it might be going faster than the speed it is going in relation to the water because the water might be also moving. So for example, let's say you had a river and the river was not moving at all. The water was stationary. I'm just going to draw a river here. The water is totally stationary. Here's the trees. That doesn't look like a tree. How do you do a tree? Okay, so there's a tree. And here's the boat. And the boat is going, right? The boat's going in this direction. And let's say the water is completely motionless. So if this boat is going, say, 10 miles per hour, right? In relation to the water, it's also going 10 miles per hour in relation to the land. It's going to go past this tree at 10 miles per hour. But if the water itself is also moving, it has a slow current of, let's say, 3 miles per hour, the boat is not only going 10 miles per hour, it's going 10 miles per hour in relation to the water, but in relation to the land, it's going 10 miles per hour plus the current of the river. And if the current of the river is going 3 miles per hour, you're going to add that 3 miles per hour to the 10 miles per hour to get how fast you're going in relation to the land. So that's sort of the concept behind this. So let's actually try this problem and see if we can do it. It says a boat's speedometer reads 20 miles per hour going downstream, and it reaches its destination in 45 minutes. So it goes from A, let's just draw our picture here. So we've got point A, and it's going to go this way, and here's point B, right? And it starts here at point A, it ends at point B, and then he turns around again. He first goes from A to B, and the river, by the way, he's going downstream. So the river, the direction of the water is that direction. So when he goes from A to B, he probably is going to go a little faster because the current is helping him move faster. Then when he's going to turn around and goes from B to A, okay, he's going to go against the current. So probably he's going to go a little slower. That's my guess. And sure enough, it says when he went from A to B, downstream, he reached his destination in 45 minutes. And then when he returned, came back going upstream, it took him 1 hour. 1 hour. Okay? So that tells us there's something going on there. And the question they're asking it is at the speed of 20 miles per hour, how fast is the current? What am I saying? I'm sorry. What am I? It says, let me read the whole thing. A boat's speedometer reads 20 miles per hour going downstream, and it reaches its destination in 45 minutes. If the return trip takes 1 hour, at the speed of 20 miles per hour, the same speed, look at that, that's interesting. How fast is the current? It's current that's going to make the difference here, because the boat, according to the water, is going 20 miles per hour. But in relation to the ground around it, on each side, the banks of the river, he's actually going faster or slower than 20 miles per hour. So let's see how that works. We always start with our little box. So we're going to create our little box again to get this figured out here. So we got rate times time equals distance. Okay? Now I'm going to write this, since it's the same boat, we're only comparing, we're not comparing two different boats or two different planes we're comparing the same boat going downstream versus that same boat going upstream. And notice the distances to go from A to B and then from B to A is going to be the same. So the distances, it'll be like this. It'll be a d1 equals d2 kind of a problem, right? So we have to find our distances. This will be our d1, and this will be our d2. So we're going to first we care about going downstream. So I'm going to go downstream. So I'll abbreviate, and then upstream. Okay? So let's see. It says the boat speedometer reads 20 miles per hour. So I'm going to write 20 miles per hour. And it's going 20 miles per hour coming back as well. So I'm going to write 20 miles per hour. But I'm leaving a little space here because my speed, my rate, or my speed, is also affected by the current. All right? Now, I know I'm going to deal with that in a second. Let's see. Well, actually, let's deal with it now. It says we're going downstream. Going downstream, wouldn't you agree that the speed is going to be faster? I'm going to go faster because the current is adding to this. And I don't know what the current is. It says how fast is the current? That's the question. So the current is x, since we don't know what it is. And since when you're going downstream, that current adds to the speed. So I'm going to say plus x. When I'm going upstream, that current subtracts from the speed. So I'm going to say minus x. Now we've got the problem of time. It says it's going downstream and it reaches its destination in 45 minutes. So to go from A to B took 45 minutes. Now if I wrote 45 in here, that would really mean 45 hours. I want 45 minutes. Well, what is 45 minutes in relation to an hour? Let's see. 15, 30, 45. Oh, that's 3/4 of an hour. So 3/4, I could say 0.75, couldn't I? Actually, 3/4, maybe 3/4 is easy. I'll just say 3/4. Because I noticed times 20, that's really easy to do. So that's what my time is going downstream. Coming back, it's 1 hour. So I'll just put a 1 there for 1 hour. All right, and then my distance is merely going to be this times this. This times this. So my distance for downstream is going to be 20 times 3/4. Let's just figure that out for a second. 20 over 1 times 3 over 4. The 4 goes into 4 once. 4 goes in that 5 times 3 is 15. So we're going to have 15 plus 3/4 x. Okay? I just used the distributive property. This one, 1 times this is just this. So I'm going to just rewrite that. 20 minus x. And remember what we decided. Our distances are equal to each other. They're exactly the same thing. Therefore, I can write my equation. This equals this. So we have 15 plus 3/4 x is equal to 20 minus x. Okay. Now, I am going to add x to both sides. Add an x to both sides. That gives me 15 plus 1 3/4 x's. I'm going to put 1.75 because that's the same thing. Equals 20. Okay, now I'm going to subtract 15. Subtract 15. Draw my line. I've got 1.75x is equal to 5. Now I just need to figure out what that is. 5 divided by 1.75. I'm going to quickly grab my calculator if I can find it, so I don't have to do this the longhand way. So 5 divided by 1.75 is equal to 2.86. So x, the current, is approximately 2.86 miles per hour. And that's it. That's how you solve. So then of course you have to write your answer. Since it's a word problem, you've got to write your answer in words. So it says how fast is the current? You say the current is 2.86 miles per hour. And you put it in a box and you are officially done. And that's it. That's how you do it. It works the same way with headwind, with a plane going with a tailwind and with a headwind, where you're going against the wind. Works the same way. You're always going to have the speed of the vehicle first, and then you're going to add or subtract the speed of the current, because you're never going to have the current. You're never going to be subtracting the speed of the vehicle from the current. It's always going to be the vehicle first, plus the current or minus the current. And that's it. All right, thanks.